SwayamPrabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. We are going to discuss about the very interesting and useful process, chemical machining, chemical micromachining and photochemical micromachining, both macro as well as micro. Acknowledgement, advanced machining processes, where this has been discussed to some extent. Deepshika Priyadarshini, MTech student of IIT Kanpur, who delivered a lecture on micro photochemical machining. Mr. A.C. Mathur, Head Mechanical Design and Analysis Division, ISRO, Ahmedabad. Quite a good part of his lecture has been shown over here, reproduced over here, and he delivered a talk in the course on micromachining held at IIT Kanpur. Organization of the talk is Introduction to Chemical Machining, Micro and Macro both, Micro Photochemical Machining using photoresist method, Classification of Chemical Machining Methods, Applications and conclusions. Please note it carefully. Here I am not going into the electrochemistry of the process. I will just give a general principle, setup, description and some application. Introduction, chemical machining. It is an ancient process being used for engraving metals, for making ornaments and other products, specifically in India. It removes material in a controlled manner by the application of maskant and etchant. Removal of the material is by etchant, and identification of the area from where material is to be removed is done with the help of the maskant. Maskant does not allow etchant to reach and react with workpiece material to dissolve it, while etchant dissolves workpiece material by chemical action. Some salient features of chemical machining are as follows. It can give you shallow depth of removal of material, normally in terms of microns, as good as up to 12 micron or so. Low cost of tooling and equipment, low production runs, and material removal rate is quite low, 0.1 millimeter per minute. So this clearly indicates that it is not for bulk material removal, rather it is just for creating micro nano features on the component. Burr and stress-free process, because in the one of the lectures we have discussed deburring and other things. So those kind of the burrs are not formed in this particular process, and it is stress-free, no thermal, no residual, no mechanical stresses are developed in the chemical micromachine components. Complex designs can be fabricated with this particular process. This is very special characteristics and advantage of this particular process. And thin plates as thin as 5 micrometer can be processed by this particular process, and this is very unique advantage and application of this particular process. Chemical macro micromachining. chemical machining, micromachining, here surface is patterned by coating it with a material known as or named as resist, forming the desired stencil pattern in the resist coating. This resist simply means it does not get affected by the agent, transferring the pattern into the surface. Whatever pattern you want to create, micro, nano or macro feature on the surface, that pattern has to be transferred on the surface of the component to be machined. A variety of energy sources are used for exposing the resist pattern, such as X-rays, electron beams, ultraviolet rays, etc. You can see over here, this is the ultraviolet rays are there, or ultraviolet light is there. This is the mask. This is the open space. This is the open space. This is the mask. Then you have photoresist. This is the photoresist, and then you have the silicon wafer over here, and this is the silicon oxide layer over here. This is important to note and remember these different constituents, so that later on we can understand the whole process properly. Mask aligner is very important, so some instrument is used for that purpose, and this is the photographic view of that mask aligner. Classification of chemical machining methods. Steps to be followed before going to classification. Clean the workpiece first using alkaline solution and then with fresh water. Apply the maskant coat by one of the following methods: cut and peel method, screen method, and photoresist method, that is also known as photochemical machining. Same thing again repeated here: cut and peel, screen, and photoresist method. Apply the maskant by one of these three methods. Dip the workpiece in the etchant bath and let it be there for the desired time. This time is decided based on how deep you want to create the feature or the depth of the feature. Take the workpiece out from the etchant bath. Once the depth has been achieved and feature has been created, you take out the workpiece from the etchant bath, remove the maskant because you have applied the maskant layer, which is acting as the resistance to the etchant, if any, and wash under fresh water before really taking the component for assembly or use. Pictorial view, you can see over here, this is being controlled with the help of the motor, up and down motion of this. This is the area to be machined. B is to be written on this workpiece. This is the workpiece on which B is to be written. Here you have etchant resistant lining. This lining is the etchant resistant because you are having the etchant over here, and this etchant should not react with the container. Here is the heating coil to control the temperature of the etchant, because temperature of the etchant is going to control or going to affect the material removal rate. And then you have the agitator or stirrer, because whatever reaction products are formed, they should not get accumulated at a particular place. So you need the agitator or stirrer so that it gets distributed in the whole etchant bath. And this is the area to be machined, and this is the etchant container. Same thing shown over here. This is the maskant coated area where you have to remove the material from this area with the help of the etchant. Maskant peeled off. Here this peeled off, it is already peeled off in this figure also. In this figure it has been peeled off from marked area for etchant reaction, because here etchant will react with the workpiece surface and remove the material, as shown over here. Agent has, this area has been marked over here, and this is the workpiece. So agent will react or remove the material from this workpiece surface only in the area where there is no mask end, because here is the mask end, no material will be removed beneath this. Here is the mask end, no material will be removed beneath this, like this. So cut and peel method. Chemical micro milling or chemical machining milling operation. This is part to be milled. Certain feature is to be created on this part by milling operation. Part with mask applied. On this part, maskant has been applied, and wherever you want to mill it or remove the material, their mask is scribed and stripped. From here the mask has been removed or peeled off, so that agent will react on the workpiece surface over here only, and the material will be removed and the feature will be created. So this is the one part being milled, and after removing this, you can see the part feature has been created on the part. This is the feature that has been created on this particular part. So you can see this is the feature created on the part. Additional area of mass scribed removed. So these are the various steps again. Start, dip after cleaning the workpiece, dip or spray workpiece to apply the photoresist. Now there are various techniques by which you can apply the photoresist. One of them is the spray. Then negative, apply to surface. Apply master pattern over, this is the master pattern, both sides of the resist exposed. If you are removing the material from the both sides, then you apply this photoresist on both sides or master pattern on both sides as shown over here. Now you can clearly see photoresist developed and exposed areas of the resist removed. So these are the areas where there is no photoresist, from where the material is to be removed. Now you can see over here, this is being machined, and this is the curved shape that you are getting over here, like this, after removal of the material by the agent. And this is cross sectional area, as you can see over here. This is the kind of the shape you are going to get. So this is how this process works, and you can create micro features with this process very nicely, and this is commonly used in the industries. Cleaning. Now this is the maskant to be removed. Now let us see here. To ensure proper adhesion of maskant on workpiece, chemical cleaning is needed of the workpiece, so that this maskant properly adhere on the workpiece surface. If it is not properly cleaned, then this maskant will not adhere and it will get separated out. If debonding takes place, stray cutting. Now this is the debonding has taken place, and you can see over here, and stray cutting will take place over here, because agent will come in contact with this, and the material removal will take place from the space or the area where we do not want the material to be removed, but it takes place due to the debonding, etc. Cleaning of the workpiece surface is the function of maskant, workpiece material, and depth of cut. Cleaning of porous material is very difficult, and it is not very effective in most of the cases. For higher material removal rate, agitate and heat the agent in the container. I have already told you in the earlier slide that if you raise the temperature of the agent, material removal rate is going to be higher, and if you agitate or stir the solution or the agent in the container, then whatever reaction products are there, they will get distributed, and you will get properly machined component. How to maintain high material removal rate? filter the agent before recirculation, periodical addition of new agent. Now what normally is done is that after machining for few components, say you take 30% of the agent out and add 30% fresh new agent, and this is how you can continue, that is periodical addition of new agent to the agent bath, discarding some percent of used agent. This may be 30%, 40%, 20% depending upon your experience, and you can conduct some trial and error testing also for this purpose. Material removal takes place in two directions, downward direction as well as lateral direction. Downward direction will result into the depth of cut, lateral direction will result into the undercut. So undercut is not desirable, but it is a part of the process, you cannot avoid it. You will see it what it is. Undercut is the function of depth of cut, agent, type of agent you are using, properties of the workpiece material, and etching time. You can see over here in this figure, this up to this point you have the maskant layer or photoresist layer, and cutting should be done only up to this point. As per our requirement, cutting should have been done only up to this point, but it is taking beyond that, and that's why this portion or this length is known as undercut, and this part is the depth of cut from the top surface to the bottom surface, wherever this depth of cut is varying along the length, but here it is like this. H factor, very important factor in chemical machining, undercut divided by depth of cut. This is the undercut divided by the depth of cut. For uniform machining, do not allow gas to be trapped in the electrolyte, otherwise you are not going to get uniform proper machining, because gases are produced due to the chemical reaction and they should not get trapped. So you can avoid this by agitating the agent or stirring of the agent. Maskant protects the workpiece surface from chemical attack and chemical dissolution. Cut and peel method, we have seen this is the maskant, this is the workpiece. Now remove the maskant from the portion where from you want to do the machining, wherever you want to do the machining. So the maskant has been removed from this part as well as from this part, from here as well as from here. The maskant has been removed. This is the surface to be etched. Now if you see here, this is the machine component, and you can see clearly etched surface with undercut. This is undercut, this portion is undercut, which I have already explained to you. From this part to this part, this is the undercut, and it is, you can clearly see you are getting the tapered part, not the straight sided part, while our requirement is straight sided part, but you are getting taper, and this is the taper angle which you can define it. We want minimum taper angle, or another solution for this which I have not discussed here is that you design the undercut in such a way and time that you get a better product, but some taper angle will always be there in case of this particular process. Neoprene, butyl or vinyl based materials are used as a maskant. Dipping, spraying or flow coating can be used, because we are going to coat the maskant over the surface. So you can do it by dipping in the bath or spraying with the help of the nozzle, etc. on the top surface. As you can see, this is the one coating, or flow coating is there. You can use one of the methods. Coating thickness varies usually from 25 micron to 130 micron. This also depends upon the kind of the maskant you are using and kind of the agent you are using. First, apply to the entire surface of the workpiece, means whole surface is masked first and then cut and peel off from the area to be exposed to the agent for machining. That is what you can see here. This is first applied to the whole surface, then it is peeled off from these areas where from the agent will remove the material and give you this kind of the machine component. Accuracy usually obtained lies in the range of 130 micron to 750 micron. Machine depth depends upon etching time. How deep it is going inside, it will be decided by the etching time, and usually tapered workpiece is obtained, that I have shown to you here. For stepped component, this is very good advantage of this particular process, that stepped components can be made by this particular process in a much easier way. Good for large sized products, batch production and large depth also. I will show you in photochemical machining that very large sized antennas can be comparatively easily made by photochemical machining, which is a part of chemical machining. Screen printing method. Screen printing is good for high volume production, low accuracy, low etching depth and large part size, because I have already shown to you, because tapered component is obtained and undercut is taking place. So all these are responsible for low accuracy of the machine component. Screen blocks off area to be machined, because screen printing, so wherever you want the machining to be done, that part is first blocked by the screen, the rest of the area is covered by the mask end. So wherever screen is there, you remove the screen, then etching will take place. Press the screen against the surface of the part and then roll over the mask end. You can spray it, you can roll over it, whatever way is available or whatever method is available in your shop. Remove the screen and dry up the part by baking or heating, and then now do etching by dipping it in the etching bath or etchant bath, and then go for cleaning purposes. Photochemical machining, also abbreviated as PCM, steps to be followed. This is very important process and very commonly used in electronic industry. For complicated and accurate surfaces, enlarged drawing accounting for overcut, as I mentioned, we have seen already undercut. So you have to account it at the design stage. So you prepare the enlarged drawing of this, then produce reduced and accurate master transparency or photo master film, that is also known as photo master film. So first you enlarge it, then reduce it, or use laser pattern generator. Clean the workpiece thoroughly, remove dirt and oxides, apply a thin coating of photoresist. It is a agent resistant material which resists the agent, and dry by baking. Hold photomaster and workpiece together in intimate contact. After developing this, remove the coating from the areas where etching is to take place. That we have seen in cut and peel method also, that the area from where material is to be removed, it has to be exposed to the agent. Etch, strip off residual photoresist and inspect. First do the etching for the required time depending upon the depth of penetration, and then strip off residual whatever photoresist is left over there, just like we remove the mask end for cleaning. So you remove the photoresist, residual photoresist or whatever photoresist is left over there, and then clean it and inspect it. Photochemical machining is schematic representation of steps to be followed. Most of them I have already shown to you in the earlier slide. Prepare enlarged drawing accounting for undercut, then reduce this drawing and make master transparency, clean the workpiece thoroughly, then apply the photoresist, dry by baking, heating, and then hold the reduced photomaster and workpiece together, because photomaster has to be kept so that the portion from where you want to remove the material is removed and rest of the portion remains unaffected. Throw ultraviolet light, develop and remove undesirable coating, develop this part and then remove the undesirable coating, and then etch by dipping in etchant. Remove photoresist after machining, remove photoresist, inspect it, and then you get finally machined component. Some process variables. Maskant. Choice of maskant depends on these factors. This is very important because unless you select a right kind of maskant, you are not going to get the desired workpiece properly machined. Choice of maskant depends upon the type of etchant, because etchant should not react or affect the maskant. Type of workpiece material, the maskant should not react with the workpiece material, otherwise whole component will get damaged. Then stability of maskant at high temperature, because we have already seen that we are going to increase the temperature of the etchant for increasing the material removal rate. So the maskant should not get affected, it should not change its properties at high temperature at which etchant is there, and maskant should not have any chemical effect on workpiece. This is very important property of the maskant, that it should not react with the workpiece, otherwise it will get damaged. Etchant changes metal into material salt, because chemical reaction takes place between the etchant and the workpiece material and it prepares material salt, and that is residue and it has to be removed from the etchant bath. FeCl3 is used as the etchant for aluminum, copper, nickel. FeNO3 is used for silver. HF is used for titanium. HNO3 is used for tool steel. So what I mean to say here is, for different workpiece materials you have to have different type of the etchant. Selection of etchant factors to be considered. Surface finish, depending upon the surface finish that you require, etchant has to be selected. What material removal rate you need, what depth of penetration you require, and what is the type of the workpiece material that you are going to machine, and then type of the maskant that you are using. We have already seen that etchant and maskant should not react with each other, otherwise you will not get the desired results. And damage to workpiece should not take place, if any. And availability and cost are prime concern for any manufacturing process, so they should be taken care of properly. Advantages: good finish, close tolerances. Now these are all qualitative terms, please don't get confused. Good finish, when I say there are process, these are the qualitative terms, not the quantitative terms. Tapered and stepped workpiece can be fabricated, do not require highly skilled operators, not operations, highly skilled operator, it should be operator. Machining of a tapered and stepped workpiece pieces is possible. This is the unique advantage of this particular process, that in one go itself we can have the final product as the tapered product as well as the stepped product. You can see here, this is the tapered product, and we have already seen in the earlier slide that whatever hole you were drilling, they were tapered, and these are the stepped components. which you can easily machine by this particular process. Chemically machined workpieces, these I have shown while discussing electrochemical grinding and other processes also. So what I am trying to show here, these components can be easily machined by photochemical machining or chemical machining, and then they can be deburred if any burrs are there because of conventional machining. Photochemical machining or chemical machining is not going to give any kind of burrs. Limitations of etchant in chemical machining, only a few metals can be machined. Evolved gases are there, and because of these evolved gases, uneven material removal may take place. So it has been suggested that you should stir the etchant or vibrate the etchant so that uneven gases are out from the etchant path. Attack the surrounding equipments and human beings. Whatever the vapors are or gases are removed due to chemical reaction, these gases, they come in contact with the equipment and the human beings, and they, both of them, equipment as well as human being, both of them suffer. So for this purpose, you should very carefully design exhaust system, and once exhaust system is there, then only the equipment and surrounding can be safeguarded. And exhaust system should be such that you don't throw the gases in the open air or environment, otherwise government restrictions are there. So you should put them and further get some chemically reacted and they produce the sludge rather than you throw them out in the open air, otherwise legally you may be in trouble. It definitely gives low material removal rate. Etchants are usually corrosive in nature, toxic in nature, hence harmful to the surrounding equipment and operators as seen in the earlier part. Differential machining of alloys leads to surface finish. Now this is very important, differential machining of alloys, because alloys have many components and different components will have different material removal rate, and that different material removal rate is called as differential machining. And once differential machining is taking place, you will not get good surface finish. It is very simple to understand. Suppose this is the one and you have these different components in the composite material or alloy, then this will be removed up to this point only, this will remove the material up to this point only, and this may remove the material up to this point only, depending upon electrochemical equivalent and the characteristics of these constituent materials. So finally you will get the rough surface or very rough surface in such cases. Micro photochemical machining, photoresist method. Photochemical machining, PCM is a chemical method used for shaping and sizing the materials. It mainly consists of photos, that is negative, or it can be positive also, and chemicals. The unwanted metal from the job is removed or the workpiece is removed by etching process, resulting into the required shape and size. Designed circuit pattern or contour, pocket, etc., PCB, printed circuit boards, etc., they are machined or they are rather prepared by this particular process very efficiently and accurately. Applicable for both macro as well as micro machining. Elements of photochemical machining system. Workpiece, for example, copper coated PCB printed circuit board. Artwork, graphics, drawing. Exposure unit for photoreaction. Master a photonegative. Maskant, photoresist or photosensitive film. Lamination, machine to coat workpiece with maskant, because maskant has to be coated or sprayed or cut and by different methods on the component. Agent chemical solution that reacts with workpiece and removes the material from the desired area only wherever there is no photoresist or no maskant. Developer chemical solution is done, developing of the film is done in the chemical solution. Agitator, as I have mentioned earlier also couple of times, it stirs the solution to distribute the reaction product. This is very important to distribute the reaction product, otherwise you are not going to get uniform machining and the desired dimensional tolerances on the component. So agitator stirs the solution to distribute the reaction products in the solution for enhancing the reaction rate. Tank is there for cleaning, etching, washing purposes. Tank is there for removal of maskant also, and you should have temperature controller in the agent that will really improve the accuracy of the component being machined. Steps to be followed in photochemical machining, that is PCM. Workpiece cleaning, we have already seen them. Application of the photoresist, dry by baking or heating, artwork placement over the workpiece, that is the generation of enlarged drawing to account for undercut, then reduce this enlarged drawing as master artwork so that undercut is taken care of. Ultraviolet exposure of the photoresist, development removes undesirable coating from the component or the workpiece, and etching of the substrate takes place in the etchant bath. It removes remove the photoresist, and then cleaning of the substrate, and finally you get the product, machined product of the desired shape and size. Photochemical etching process. Now let us see here. Copper coated Kapton film is here. This is the copper, this is the Kapton film, and here is the photoresist. The application of the photoresist. After this, photonegative is placed over here, and then light is thrown over there. So resist exposed through the negative. This is the negative photoresist. Photonegative written over here, and then resist developed. After the development of the resist, you get this kind of the photoresist, right? Because photonegative has been removed, and this is the layer or the copper to be machined. Then etching, it is placed in the etchant bath. Then you get this kind of the component, etched film with remaining resist. Resist is remaining. This is the etched film, copper, and this yellow color, that is the machined component. And you remove the photoresist, then you get the final product, finished graded Kapton film. So this is very interesting, and micro featured components are produced by this. Now here you can see here composite structure of dry film resist. You can see here different components, same, but we have seen earlier, that is the cover sheet, polyester, this is the 25 micron, around 25 micron. Then you have the resist film, that is 12 to 70 micron depending upon your requirement, and then you have the copper foil over here, and this is the base material. Etchant dissolves metals into metallic salts. Common etchants are here. We have seen already this in the other slides. FeNO3 for silver, HF for titanium, HNO3 for tool steel, and chromic acid mainly used for copper. So different metals require different kinds of the etchant. So it is not necessary that each material or metal can be photochemically machined. You have to have proper etchant for that purpose, and proper maskant also for that purpose. Selection factors for etchant: required surface finish, what type of maskant you are using, material removal rate, depth of penetration, type of workpiece, damage to workpiece, availability and cost. Some of these things we have discussed in chemical machining, which are more or less the same as for photochemical machining, except some differences. Type of maskant, wet type maskant and dry type maskant. 12 to 70 micrometer thick films supplied by DuoPont and Dynachem. They are used with lamination. Properties of maskant: photoresist. It protects surface from etchant, resistant to etchant. We have already seen that photoresist is remaining there, and wherever photoresist is there, no material removal is taking place. Only from the place which is open to the etchant, the material removal is taking place. Light activated maskant, that is there, and it is opaque. So easily removable after etching. This maskant can be easily removed after etching. No chemical effect on the workpiece, and stable at high temperature of the bath. We have already seen in the properties of the maskant and the etchant. In the properties of the maskant, we have already seen that it should be stable at high temperature, and etchant also should be stable at high temperature, because we are going to heat it to improve the material removal rate. Now you can see other same thing with better picture. Resist is there. This is the surface or the area which is to be exposed to the etchant, and again resist. This is the base material, and this is the Kapton film, and this is the undercut. Now this much material has been removed, and you can clearly see this is the undercut, which is undesirable, but it is a part of the process. General guidelines for etching: gaps are difficult to image than lines. Specify gaps larger than associated or normal line width. Radiused corners are preferred over sharp corners, because in this process you cannot prepare the sharp corner. They have to be radiused, doesn't matter inner corner or outer corner. Minimum line width is determined by resist thickness. Minimum job thickness should be 2 times of the resist thickness. This is very important to note while designing resist for the purpose. Factors affecting etching rate: depth of cut, acid concentration, immersion time, temperature, metal to be cut, and etch factor. So all these factors, etch factor is the result of that. So all these factors, they are going to control the etching rate, or you can say in other words, material removal rate. Etching defects are there while you are etching. Certain defects are observed in the machined or etched component, like cracks in the lines. They are observed many times. Pits on the metallized surface are also observed. Rounded corners on the lines instead of good metered corners. Non-uniform line width and undercutting. So these are the defects, or you can say limitations of the etching process. Cleaning process: oil waste soils, vapor degreasing, ultrasonic cleaning, water soluble soils, deionized water, high purity alcohol, no hand handling. Be careful, otherwise you may get injured. Non-metallic tweezers or rubber finger cuts. Photoresist: a photosensitive plastic coating material, when exposed to ultraviolet light, it becomes hardened and becomes resistant to etching solution. That's why you must have seen in the earlier slide, photoresist remains while etching. Negative: an emulsion that becomes insoluble when exposed to ultraviolet light. This makes the desired pattern hard and resistant to the etching chemicals. Positive, an emulsion that is soluble in developing solvents. This resists, duplicates the desired pattern, and hence the name positive. So you have to be careful while selecting whether negative or positive, and accordingly you have to design the whole system. How to apply the photoresist? By immersion, by spraying, by spin coating, or by lamination. Positive versus negative processes. The decision to use positive or negative process depends on the final application of the product. Generally, positive photoresist is used for the narrow gaps between the lines. Limitations of the process. The etchant vapors are very corrosive and sometimes toxic. It requires careful handling. Owing to facilities not available at a single place, parts have to be transported from place to place. Useful only for few metals because of non-availability of etchant and maskant, and material removal rate is very low compared to other advanced machining processes or conventional machining processes. Advantages of PCM: highly skilled operators are not required, good surface finish, closed tolerances, uniform material removal. Again, please note, I have already mentioned these are all qualitative terms: closed tolerances, good surface finish, not quantitative. While really selecting the process, you should quantitatively compare these characteristics with other processes quantitatively. Complicated and curved shaped parts can be made by this. Intricate and thin surfaces can be obtained. Repeatability of the process is good. Stepped machining is possible. We have seen stepped components already and tapered components. No problem of tool wear and tool breakage, as we have seen in case of conventional or traditional machining processes. Applications: aviation industries, printed circuit boards very commonly used for that, jewelry making, turbine engine components, pressure vessel, bulkheads, etc. Chemical milling is used for production of blind pockets, etc. Chemical blanking is used for production of through cavities, through holes, through slots, etc. Aluminium, chromium, copper, nickel, steel, lead, zinc, etc. they can be easily machined. Chemically machined workpieces, I have already shown them in the other slides while discussing electrochemical grinding and other processes. They can be machined or they are being machined by photochemical machining also. So one product can be machined by different processes, so it doesn't matter. Applications further: jewelry designs, rigid PCBs for ground and space systems. This is very important application. Development of flexible PCBs, printed circuit boards for ground and space antennas, pockets in metal parts to reduce the weight. If you want to create the pockets, this process is very good for producing the pockets in the metallic parts. Development of gridded antenna for satellite communication, very important application using photochemical machining method. Now these are the kind of the antenna that are being prepared in India also at ISRO, Hyderabad. Grid manufacturing requirement. Thickness is around 0.300 millimeter plus minus 0.010. Width of grids 0.381 millimeter plus minus 0.01. Distance between grids 1.9. You can see over here grids over there. Grids to be generated on a doubly curved surface. This is a doubly curved surface on which grids are generated, and it is very difficult to produce the grids by any other method other than PCV. Other than photochemical machining. A special computer program was developed for changing 3D to 2D surfaces. Good peeling strength, because this is the 3D component, it has been converted into 2D, so special programs were developed for this purpose, and good peeling strength and no corrosion of the surface. And this was done at ISRO, Ahmedabad, and this is from the lecture of Professor Mr. A.C. Mathur from ISRO, Ahmedabad. I will show you some more examples. Inset spacecraft, where this particular process has been used. This is again antenna, 14 meter diameter. This is another one, KFRP there, and then metallic layer is there which has been gridded by this particular process. So material to be removed using laser etching, CNC milling. Antenna is the most important element of a satellite communication system which is used to transmit and receive microwave signals. Antenna mainly consists of a reflector, feed and transmission waveguides. Antenna for ground stations, fixed earth station, road and air transportable, portable stations, all kind of stations are there. You can see this is the antenna, ground antenna. This one antenna is here. Another antenna, as you can see over here. This is the antenna. Another one. These are all the pictures taken from the lecture of Mr. Mathur of ISRO, Ahmedabad. You can see another ground antenna, and they are made by ISRO using this particular process. Most of them are made by them. Again, vehicle is there, antenna is there. Antenna for spacecrafts are printed circuit boards are prepared using this particular process very carefully and very nicely, as you can see over here. Liga process, I am not going to discuss this process in detail, but very useful process. It is a German term. It utilizes a useful industrial application of synchrotron radiation. Fabrication of extremely tall 3D microstructure with a large aspect ratio using Liga process. Movable components can be fabricated directly by using sacrificial layer technology. I am not going to discuss in detail this particular process. It needs separate lectures for it. Same is true for TIGA. TIGA, Teflon included etching, galvanic forming. Etching rate is of the order of 10 to 100 micrometer per minute. So you can imagine how slow it is. Processing takes much shorter than that required for the deep X-ray lithography process, a completely dry process. No more, I am not going to discuss it in detail. Conclusions: chemical machining and photochemical machining both are applicable for macro and micro machining. We have already seen some of the applications in both macro as well as micro. It has low material removal rate and shallow depth. It has applications in different high-tech areas which I have already mentioned to you. Thank you very much. Thank you.